In today's fast moving world, there is very little time to listen. So much so that we don't even pay attention to what our heart has to say. So here we are, building a circuit which you can happily carry around with you anywhere you go to exclusively listen to your heart and tell you how it feels within. What we have built here is a portable cardiac dysfunction alert system. As you can see, here is an overview of our concept. A specially designed and carefully tuned ECG amplifier circuit forms the first part of the system. This is followed by a digital transmitter section which wirelessly sends important digital data to the smartphone. In the smartphone, we have used a machine learning algorithm to detect any anomaly in the ECG waveform, and in that case, it promptly and immediately sends an alert message to the registered hospital. So, as we were speaking, the initial stage is the ECG amplifier circuit, which receives analog electrical signal variations from the heart of the user, amplifies it, and elegantly filters any unwanted noise. It consists of three stages: the instrumentation amplifier stage, the low pass filter stage, the band pass filter stage, and the level shifter circuit. Three ECG cables come out from the PCB to the body of the user to tap the electrical signal variations through AGCL electrodes and pass it on to our circuit. The instrumentation amplifier, with a gain of approximately 1000, amplifies these signals in microvolt range to levels that can be conveniently handled later on. Input offset voltage of 50 microvolts for INA 114 serves to be ideal for our purpose. The low pass filter with a cutoff of 16 Hz has been carefully designed to avoid missing any useful information and to eliminate the 50 Hz power frequency noise. Further, to avoid noise due to drift in DC supply, a bandpass filter has been cascaded as shown. This is also done to eliminate any unwanted high frequency noises. Then, a level shifter circuit has been used to bring all voltage levels above zero level so that a microcontroller does not receive negative voltages. The batteries shown have been used to power the circuit, and the voltage regulator at the right is used to get 6 volt regulated supply for a circuit. The output from the ECG amplifier section is received by the MSP430 launchpad. Here, the analog signal variations are converted to discrete form using the 10-bit ADC module present in the microcontroller. The UART module in the MSP430G2553 is used to send these digital samples to the Bluetooth module. The Bluetooth module acts as a master to the Android smartphone, which connects with it and wirelessly sends the data. In the smartphone is where all the analysis of the ECG waveform and the corresponding measures taken. Here, an Android application has been developed by us for this purpose. The application continuously searches for the paired Bluetooth device. When it finds the device, a connection is established between them. The application receives the ADC data via Bluetooth and plots the graph continuously. In case of an anomalous waveform being detected, the GPS coordinates of the person are extracted and sent via SMS to the registered hospital. Now we shall move on to the working of the circuit. We are going to observe the ECG waveform on the DSO. A person has been wired up for the setup. Now you can see the ECG waveform on the DSO. It is observed to be a very clean one, devoid of any noise. Zooming in on the DSO, you can clearly observe the P, Q, R, S and T portions of the wave. Now we shall move on to the packaging of the system. We have thought of two layers inside the box. The bottom layer consisting of the ECG amplifier part and the top layer consisting of the digital transmitter section. This is the battery pack which is used to power the MSP430 microcontroller. As you can see, the components fit inside the box perfectly. These ECG cables have been cut short to be attached to the body of the person while he is moving. This box is what the person shall carry while he is in motion. Now we shall move into the section which has been consistently missing in most of such systems nowadays, that is the element of portability. As you can see, this bag contains the box about which we had discussed earlier. 3 ECG cables run out from the box to the body of the person, one below the left collarbone, one below the right collarbone, and one below the diaphragm on the left part of his body. This is how we intend to make the system portable. As you can see, this is the wireless ECG graph as obtained on the Android application. The ECG graph is that of the person walking in the background. The graph is of normal sinus rhythm. You can see that the graph obtained is a very stable one and does not easily get affected due to the person moving around or other common actions. Support vector machines, which is a machine learning method, has been used here for the detection and classification of the ECG waveform input to it. The process has two stages: training the machine, in which a large number of real-life ADC samples from the MIT BIH database corresponding to the disorders have been collected and used for running the program on a laptop. The output of this process is a model file which is stored in an external SD card inserted in the smartphone. Using this model and the input samples obtained through Bluetooth, it categorizes the test sample, and if an anomaly is detected, the GPS coordinates using the GPS module in the phone are extracted and an alert message is sent to the registered hospital.
In order to simulate the situation of a cardiac dysfunction, we are sending the datasets corresponding to ventricular tachycardia, which has been obtained from the MIT BAH database as ADC samples using MATLAB. These samples are sent to the Bluetooth module, which in turn streams the information to the smartphone for further processing. Inside the smartphone is an application which has been developed by us, which receives these ADC samples and plots a real-time graph. The app has been shown to be open now, but it can always run in the background, consuming very less CPU power. Once the app has started, it can remain connected with the Bluetooth module and plot a graph on a real-time basis. Now, you can see the graph of the disorder, namely ventricular tachycardia, being displayed on the screen. As this is an emergency, GPS coordinates are extracted and sent through SMS to the registered hospital. The message contains information regarding the name of the disorder and the GPS coordinates of the patient. An ambulance can be sent to the location having these coordinates, and other emergency measures can be taken.